Module 3 Endurance Limit Modifying Factors. In the previous module, we saw that the endurance limit of a material is very important for considering the fatigue strength of the material. And we have also seen that endurance limit of the material was found out by conducting test in rotating beam machine. Also, we have seen that the beam specimen is prepared very carefully and tested under controlled conditions. That is, specimen is prepared very carefully and tested under controlled conditions. Closely controlled conditions. Therefore, the endurance limit of mechanical or structural members do not match the endurance limit values obtained in laboratory. Endurance limit of mechanical or structural components do not match the endurance limit values obtained in laboratory. That is because of the factor we just said above, because the laboratory specimen is prepared very carefully and it is tested under controlled conditions. But in actual case, the member will not be prepared carefully and it is not tested under the controlled conditions. Therefore, the endurance limit will be varying. And the various other factors which causes this difference in the endurance limit values can be attributed to material, composition variability, or we can say inhomogeneity of material. In laboratory specimen, whatever material we use will be a very specific and very composition will be very homogeneous. It will be a very homogeneous material. But in actual conditions, when we use a material, it need not be homogeneous. So that will affect the endurance limit of the material. Another one is a manufacturing process used. That's a heat treatment. Surface conditions, stress concentration, etc. We have seen that in a laboratory specimen, when we found out the endurance limit in the rotating beams machine, the surface finish was very good and there was no stress concentration. But in actual components, when the surface finish is less and stress concentrations are there, then the endurance limit comes down, because we have seen that fatigue failure is a failure which originates from the surface. So the surface finish will play an important role. If the surface finish is not good, the endurance limit of the material will be less. Then maybe the environmental factors. Factors like temperature, corrosion and stress states. The environmental conditions also affect the endurance limit of the material. Then finally, the design. There is size, shape, and the stress concentration. We have seen that fatigue cracks develop from the surface. Therefore, larger the size of the specimen, larger will be the surface area exposed for the crack propagation. Therefore, the chance of fatigue will be more. Therefore, the size, bigger specimens will have a lesser fatigue limit. Therefore, that also affects the endurance limit of the material. Therefore, we can say the endurance limit of mechanical members gets modified by many factors. So that we can write as SE, that is the endurance limit of the mechanical member, is equal to KA, KB, KC, KD, KE, KF. I'll put KG because KF we are using somewhere else, into SC dash, where KA is the surface condition modification factor, KB is the size modification factor, KC is a load modification factor, KD is a temperature modification factor, KE is the reliability modification factor, and finally KG, that is a miscellaneous effect. Modification factor. And SE is the endurance limit or EL of member in use, and SE dash is a rotating beam specimen endurance limit. Therefore, the endurance limit which we have to take for calculation is now SE, and that is getting that is nothing but the rotating beam specimen endurance limit modified by many factors: surface condition factor, size factor, load factor, temperature factor, miscellaneous factors, reliability factors, and miscellaneous effects factors. So we have to see what are these factors. So we have seen that the endurance limit of a mechanical member is nothing but the endurance limit of the rotating beam specimen modified by several factors like Ka, Kb, Kc, Kd, Ke, Kf, Kg. We'll see the first factor, which is nothing but the surface condition modification factor. The surface finish of a rotating surface of a rotating beam specimen is highly polished, and the surface modification factor depends on the quality of finish of the actual part surface. That is, surface of rotating beam specimen is highly polished. But the actual members, the surface finish will not be the same as the surface finish of the rotating beam specimen. So then the surface finish depends on the manufacturing process. The above tables shows the surface finish for various process. If it is a ground component, and the surface finish factor, we can say that Ka is nothing but A into SUT raised to B. This is an important relation. This is nothing but SUT is the ultimate tensile strength of the material, and Ka is the modification factor. and A and B are the parameters which depend on the manufacturing process. That is, if it is a ground component, the A value should be taken as 1.58, B should be minus 0.085. If it is a machined component, it is 4.51 and minus 0.265. If it is hot rolled component, A should be taken as 557.7 and B should be minus 0.718. If it is an as forged component, A should be 272 and B should be 0.995. You can see the variation of A and B. You can see that when the surface finish factor depends mainly on very much on the manufacturing process. If for different manufacturing process, you have a different value of Ka, and it is very significant factor also. This is a very significant factor. So that is about the surface condition modification factor. We have seen that it depends on the manufacturing process, and this is a wide variation of the surface finish factor depending on the manufacturing process. Now we will come to the second factor, which is the size modification factor. The size factor for axial loading is taken as 1. That is, if it's axial loading, Kb equals 1. Okay, therefore for axial loading we can say Kb is equal to 1, and for bending and torsion Kb is given as d by 7.62 raised to minus 0.107. That is equal to 1.24 d power minus 0.107 when d is less than or equal to 51 mm, and this is equal to 1.51 d raised to minus 0.157 d is greater than 51 mm. This is the relation of the size modification factor with respect to the size of the specimen. That is, if d is the diameter of the specimen, Kb is given by this relation, and if the d is less than 51 mm, if the diameter is less than 51 mm, Kb is given by 1.24 d power minus 0.107, and if d is greater than 51 mm, Kb is given as 1.51 d raised to minus 0.157. This is the size modification factor. Then we have the load modification factor. The endurance limit also depends on the type of load which we apply. For rotating beam specimen, where the bending was a load, we have seen that we have not considered any load modification factor. That is just because load modification factor is 1 for bending. That is, the load modification factor Kc is equal to 1 for bending case, is equal to 0.85 in case of axial loading, and equals 0.59 for torsional loading. So it depends on the loading. The endurance limit also gets modified because of the type of loading which we do. If it is a bending load, then there is no modification. Modification factor is 1. If it is axial loading, the endurance limit of the component gets specified modified by a factor 0.85. And if it is a torsion loading, it gets modified by 0.59. The fourth factor is the temperature modification factor. We know that when the temperature becomes very high, even the ultimate tensile strength of the material also changes. This UTS of the material also depends on the temperature. And we have seen that endurance limit is nothing but 0.5 times UTS of the material. Since UTS of the material changes with temperature, the endurance limit also changes. That is, since UTS of material depends on temperature, the endurance limit, which is nothing but 0.5 times SUT, also depends on temperature. And the temperature modification factor Kd is given as St by Srt, where St is the strength at an elevated temperature and Srt is the strength at room temperature. That is, for example, the strength at 500 degrees C is strength at room temperature of a material is some 600 MPa, and at 500 degrees C it's some 400 MPa. Then we can say the factor Kd is nothing but 400 by 600. This will come to 2 by 3 or 0.667. So this way we can find out the temperature modification factor of the material. Knowing the strength of the material at elevated temperature as well as room temperature, we can find what is the temperature modification factor. Now we have the fifth factor, which is nothing but the reliability modification factor. Reliability factor is used for accounting the scatter of the yield endurance limit data for materials. We also know that the endurance limit of material, we have got a straight line, as we have seen the SN diagram. When we did the test, actually we got a scatter of lot of points like this. We got a scatter of lot of points and we tried to connect these points by some straight line. Thus we got the SN diagram of the material. Therefore this endurance limit is a very highly scattered data, and reliability factor is used for accounting the scatter of the yield data. T factor accounts for the scatter of the endurance limit data. That is, how much the data is scattered, we can know from the reliability factor. Therefore, reliability factor accounts for the scatter of the endurance limit data. And reliability factor, if it is a 50% reliability factor, we take the factor as 1. If we want 90% reliability, we take the factor as 0.897. For 95% reliability of the data, we take the KD as 0.868. For 99% of reliability, we take the reliability factor as 0.814. And if you want the data to be 99.9999% reliable, then we take the modification factor as 0.62. So in rotating beam specimen, when we have taken the reliability factor as 1. Therefore, for rotating beam specimen, can say for rotating beam test, the KD, reliability factor, was taken as 1 because we did not know about the reliability factor at that time. So we can say we have assumed the reliability factor as 1. So in other words, that means that reliability is 50% for rotating beam specimen. So rotating beam data has 50% reliability. So that is the reliability modification factor. Now we will see the miscellaneous factor. So the next factor is the miscellaneous modification factor, K. In many of the textbooks, the miscellaneous modification factor is taken as Kf. Here I am not using that nomenclature because we are using Kf for the fatigue stress concentration factor. So we should not get confused between these two. So I am using the factor Kg for miscellaneous modification factor. And the miscellaneous modification factor Kg is intended to accounts for reduction in endurance limit due to other effects, due to residual stresses, this may either increase or decrease the endurance limit. It also accounts for the compressive residual stresses, like short pinning, hammering, etc., which increases the fatigue life. Therefore, there is one important parameter, that tensile residual stresses reduces the fatigue life, whereas compressive residual stress increases the fatigue life. It also considers the corrosion is another important factor which reduces the fatigue life. Of a component. Then we have stress concentration, which also reduces discontinuities, which also reduces the fatigue life. These effects are considered in the miscellaneous effects factor Kg. So these are the 6 endurance limit modification factor. That's size modification factor, surface condition modification factor, load modification factor, temperature modification factor, reliability modification factor, and miscellaneous effect factor. In some of the cases, the factors will be directly given to you and you will have to find the endurance limit of the material. And sometimes it will be indirectly given, like if the compound is in the problem, when it is told that the compound is machine, then we have to take the surface condition factor according to that manufacturing process. And if the diameter of specimen is given, we have to take the size factor accordingly. And sometimes, in most of the cases, the size factor will be directly given to you. If it is not given, then you have to find out by the relation which we have gone through earlier, which depends on the diameter of the specimen. And load factor is 1. If it is a tensile loading, if it is axial loading or the torsion loading, we have the load factor. If it is bending loading, we don't have the load factor. So those are the important things to be kept in mind. And reliability factor is another one parameter. And mostly the reliability factor also will be given as a number. So with these things, we can see that the endurance limit of the material gets modified. Now we'll try to solve a problem so that we can understand this, or we'll be able to appreciate this in a better manner. We'll try to solve a problem. A forged steel bar 50 mm in diameter is subjected to a reversed bending stress of 250 Newton per mm square. The bar is made of steel 40C8, which is the grade of the material, which shows that SUT is 600 Newton per mm square. Calculate the life of the bar for reliability of 90% and take size factor as 0.85. Now, how do we solve this problem? Now we'll find out what is the endurance limit of a rotating beam specimen. We know that endurance limit of a rotating beam specimen, SC dash, is given as 0.5 times SUT. That is nothing but 0.5 into 600. That will be 300 Newton per mm square. Now, what are the endurance limit modification factors? Sorry. Now, Ka, that is a surface condition modification factor. What will be this? It is given as, it's a forged steel bar, and for the forged steel bar, what will be the value of Ka? Ka for forged steel bar, Ka is given as A into SUT raised to B. For A will be 272, B will be minus 0.995. So can we calculate how much it will come to? That will be 272 into SUT is 600 raised to minus 0.995. How much this will be? 272 into 600 raised to minus 0.995. It will be 0.468. Now the size factor Kb is given as 0.85. In case if it is not given, if the size factor is not given, we can take the size factor to be 0.85. If it is not given, we can find out by the formula, which is nothing but Kb is equal to 1.24 d raised to minus 0.107. Since d is equal to 50 mm, is less than or equal to 51 mm. Since d is less than 51 mm, we can take this relation for Kb and find out what is the Kb value if it is not given. Here it is given, so we will take Kb as 0.85 only. Now what other reliability factor can come here? It is told that it's a bending stress. So the load modification factor, what will be the load modification factor? Kc. We know that for bending load, the load modification factor Kc is equal to 1. For bending load, the load modification factor will be 1, and this is the size modification factor. Now what other modification factors are there? Temperature modification factor, temperature is not told, so we will not take that. Now reliability modification factor, and what is the reliability they have asked for? They want 90% reliability. So we know from the table that for 90% reliability, you can take the reliability modification factor Ke is equal to 0.897. So these are the modification factors for endurance limit. So what will be the endurance limit of the mechanical component? We can write Sc is equal to Ka, Kb, Kc, Kd is not there, so we will write Ke into Se dash. So what will this be? Ka is 0.468. K we have found out here. It is 0.468 into, what is Kb? Kb is 0.85 into, what is Kc? Kc is 1 into, what is Ke? Ke is 0.897 into Sc dash. What is Sc dash? Sc dash is nothing but 300 Newton by mm square into 300. So what will this be? 0.468 into 0.85 into 1 into 0.897 into 300. This is 107. 0.05 Newton per mm square. This is the SE of the material. Now, to estimate the life for a completely reversed bending stress, we can use the SN curve for estimating the life of the component. Now, we'll see how to use the SN curve. Now, we'll try to draw the SN curve for this above problem. We have SE, the corrected endurance limit. SE as 107.05 and the ultimate tensile strength of material is 600 Newton per mm square. And we know that how to draw a SN curve. This value will be, the starting point of this will be 0.9 times SUT and 0.9 times SUT is nothing but 0.9 into 600, that is nothing but 540 Newton per mm square. So the first point of the SN curve will be log of 540 and that will correspond to 10 raised to 3 cycles. And the endurance limit, the corrected endurance limit is 107.5, not 5. Therefore, that will be corresponding to 10 raised to 6 cycles. Therefore, for 10 raised to 6 cycles, the log is 6 and the corresponding strength is log of 107.05. And we have seen that in the above problem, the bending stress is 250 Newton per mm square. So, therefore, what is the number of cycle corresponding to this stress? So, we have to find what is the value of this x. And this we have already seen earlier. We have the equation for line as y minus y1 by y2 minus y1 is equal to x minus x1 by x2 minus x1. Here y is log of 250 minus y1 is log 540 by y2 is log 107.05 minus y1 is log 540. This is equal to x. This is what we want to find. X minus x1 is 3 by x2 is 6 minus 3. So this is nothing but log 250 is 2.398 minus log of 540 is 2.732 divided by log of 107.05 is 2.03 minus log of 540 is again 2.732. This is equal to x minus 3 by 3. So this is 2.398 minus 2.732. This is minus 0.334 divided by 2.03 minus 2.732 is minus 0.702 is equal to x minus 3 by 3. Therefore, x equals minus 0.334 divided by minus 0.702, that is nothing but 0.4758 into 3 plus 3. 0.4758 into 3 plus 3, that is nothing but 1.4274 plus 3, that's equal to 4.4274. Therefore, number of cycles n is equal to antilog of 4.4274, that is nothing but 26,754.69. So that is equal to 26,755 cycles. So this way we can find out what is the number of cycles corresponding to the strength of 250 megapascal. And important thing to be kept in mind is, in this SN curve, the strength corresponding to 10 raised to 6 cycles now is the corrected endurance limit. Earlier we did not have the correction value, so we have taken the rotating beam specimen endurance limit. So now the endurance limit of the rotating beam specimen is getting modified by various factors we have seen. So the corrected endurance limit has to be taken here, and this will be 0.9. This here will be 0.9 s, 0.9 times the ultimate tensile strength here. This will be the corrected endurance limit, and this will be log of 10 raised to 3, that is 3, and this will be log of 10 raised to 6, that is 6. And the stress which they have asked for will come here in between these two values. Number of cycles can be found out by this manner. So this completes the module on the endurance limit modification factors. In the next module, we will be seeing about the stress concentration and the notch sensitivity of the materials.